Hello everyone, my name is Junaid Mahmood. Today I'm excited to share my recent paper entitled Combining Language and App UI Analysis for the Automated Assessment of Bug Reproduction Steps. So this is an example of a bug report. At the very least, a bug report must contain three different information. First one is observed behavior, the unexpected behavior a user experienced. The second one is expected behavior, the expected behavior from the app so that the bug will be resolved. The third one is the steps to reproduce, that is, the steps that are required to reproduce a bug. The goal of providing all those information is to help developers so that they can understand, locate, and fix bugs. Reporters are often not familiar with the specific descriptions that will be useful for developers. Therefore, bug reports often contain missing information, ambiguous steps, and incomplete descriptions of the steps. Because of these issues, bug report maintenance becomes a challenging task. Because of the low quality information in bug reports, many issues arise, such as many bugs remain non reproducible, many bugs remain unresolved, there may be delays in bug fixes. Even if the bugs are resolved, many bugs still needs to be reopened because of incorrect fixes. User-facing software is largely centered around graphical user interfaces, which is one of the most prevalent types of software used in today's world. GUIs represent a significant part of the application, comprising half of the code size, development time, and maintenance efforts. Users interact with components in GUI screens to perform an operation or execute a feature in an application. In our paper, we focused on the bug reports for GUI-based Android applications. The most crucial contents in bug reports are the steps to reproduce. The marked sentences in green rectangle are the steps to reproduce for this bug report. These steps should be described with terminologies that developers would easily understand. These steps must link to the specific GUI interaction so that developers can easily understand and reproduce bugs. For example, take a look at the first example here. To navigate to the service intervals screen, a user has to click on the service intervals button here. So, click is the action here and service intervals is the GUI component, and the STR maps to one specific GUI interaction. In the second example, there is a specific button called Add Service Interval and it also maps to one specific GUI interaction. In the third example, the STR, that is I entered the information for my next oil change, requires entering information into multiple text fields and clicking on Add Service Interval button. However, all those interactions are not explicitly described in the STR, where ideally each STR should describe one atomic interaction. In this work, we aim to identify whether the steps to reproduce described are of high quality or not. To address the issues with low quality steps to reproduces, prior research provided many solutions such as generating missing STRs, automatically reproducing the bug reports, facilitating interactive bug reporting, and providing quality feedback to reporters. Among all the proposed techniques, we believe assigning quality annotations to STR is the most beneficial for reporters as they will be able to get feedback and rewrite bug reports if necessary. This proposed approach is called Euler, which first takes a bug report and extract all the STRs from the report. Then Euler maps the interactions described in steps to reproduces to programs and assign different quality annotations to generate a quality report. This report is then sent again to the reporters as feedback. However, it uses traditional NLP techniques and fails to properly map STRs to GUI interactions. To improve the process of assigning quality annotations to bug reports, specifically STRs, we proposed an approach called Astrobeer that provides quality annotations to steps to reproduces. This approach is divided into four separate steps. First one is identifying steps to reproduce from bug reports, extracting individual steps to reproduces, generating an app execution model, assessing bug report quality, and providing quality annotations to each STRs. In the following slides, I will discuss each of those steps. Let's assume we have a given bug report. We will need to identify the STR sentences from this report. To identify these sentences, we first design prompts, then these prompts are then sent to GPT-4 to identify the STRs from bug reports utilizing a prompt. We have utilized different prompt settings and chosen the best one, which we will discuss later. we have added different contexts for S2R identification. First, there can be different explicit actions that can be described in a S2R. For example, in the first sentence, the click action is described in a GUI component. Second, there can be different verbs to describe actions in a S2R. Take a look at the example, add a second service. Usually these steps require performing multiple steps in GUIs. There can be multiple individual S2Rs that are present in one S2R sentence. These are often connected by different prepositions or linkers. In this particular example, two individual S2Rs are connected by and preposition. In our approach, we separate each individual S2R with a prompt to GPT-4. Let's show an example here. In the first example, two individual S2Rs, that is open mileage tracker and navigate to the service intervals screen, are connected by and preposition. In the second example, three individual S2Rs are connected by a right arrow. To be consistent in the generated output format, we used a specific format when extracting individual S2Rs. This format contains an action and a direct entity which is connected by a related entity with a preposition. For example, an individual S2R click any button on this page. The action is click. Any button is the direct entity which is connected to the another entity with a preposition on. In order to map each individual S2R to GUI, we first created a graph-based representation of the application GUIs and interactions. In this execution model, each GUI is considered as the node and each interaction on the GUI is considered an edge. In this example, for node N1, interacting with the service interval takes a user to a different screen which is marked as node N2 here. Interacting with edge E1 takes a user from node N1 to N2. Similarly, with interacting with edge E2, the node N2 takes a user to node N3. After performing all the interactions on the screen, we will get an app execution model containing all nodes and edges. This graph contains approximately 100 to 1000 screens and relevant interaction information. In order to perform step mapping to GPT-4, we represented GUI component information in text containing actions and GUI component information. This GUI component information contains type, identifier, text, and GUI description. For example, the first interaction has action click and GUI component information has type button, identifier, empty add interval, and text add service interval. The second interaction also contains click action and GUI component information, type button, identifier, empty edit templates, and text edit templates. We provided an individual S2R and the interaction information in GPT-4 to a prompt. Then we asked GPT-4 to identify interactions from all the available interactions that map to individual S2R. For example, the steps to reproduce tap on add service interval button map to the first interactions among the available interactions on a particular screen. In a particular GUI screen, if the interactions described in S2R maps to a single interaction on a GUI screen, it is denoted as correct step. In this slide, the S2R tap on add service interval button maps to exactly one GUI interaction. Therefore, it is denoted as correct step. In this example, the S2R maps to multiple interactions in the GUIs. For example, entering the information for next oil change contains several steps. Enter oil change title, enter distance on odometer field, and tap on add service interval button. As the S2R requires performing multiple interactions, therefore this S2R is labeled as AS. There can be an S2R that doesn't require performing an interactions within the app. For example, blocking all notifications for the mileage app requires changing interactions on the device settings. Therefore, this S2R is denoted as vocabulary mismatch. We need to identify the path between two S2Rs. Consider there exist two S2Rs, that is open mileage app and navigate to the service intervals screen. However, the second screen does not appear immediately after clicking on the open mileage app. Between those two S2Rs, one step is missing, that is open the app menu. This step is the missing step between the other two S2Rs. Therefore, we annotate the second S2R as MS and considered open the app menu as missing step here. We traverse the graph utilizing a depth-first traversal approach. There can be multiple DFS paths that exist in a graph. For example, in this graph, there is a path that exists starting from node N1 to leaf node N9. In the second example, the path is starting from node N1 to node N8. we have used multiple criteria to select the best path. We prioritize the highest number of mapped estuaries in a DFS path. If two paths have the same number, we selected the shortest path because we will have less number of missing steps. In a DFS path, we do not need to traverse the entire graph. The traversal stops when all estuaries are mapped. For example, the last estuary in this example are mapped to node N9. Therefore, our algorithm will not traverse to node N10. To avoid multiple traversal for an estuary in a node, we used a visited array that has node estuary pair. In our algorithm, each node will be visited exactly once for each estuary. Finally, after assigning all quality annotations and identifying missing estuaries, we generate a quality report. Here the missing steps are marked in red, and you can also see the ambiguous step. Ideally, each estuary must describe one atomic interaction. This report will be sent back to the reporters as a feedback, and reporters can use this quality report to improve bug report. Now, I'll discuss about how we designed different prompts and asked those to GPT-4. In exactly 3 tasks, we used GPT-4. For identification of estuaries, extracting individual estuaries from identified estuaries, and mapping estuaries to GUI interactions, we designed 3 prompts. We tried with different prompts to perform each of those tasks. Now, I'll describe the prompt generation for 3 different tasks in our algorithm: identifying estuaries, extracting individual estuaries, then steps to reproduce to GUI interaction mapping. We designed 3 types of prompts. First one is zero shot. Zero shot prompt contains task description, then input data, and also the expected response format. The few shot prompt all the information in zero shot and also related examples. The chain of thought prompt contains all the information in a few shot, and we also provide rationale for input and output. So to select the best prompts, we first created ground truth data using 54 bug reports from 31 mobile apps and considered those as the ground truth data. In the identification phase, 189 estuaries were identified, and in the extraction phase, 246 individual estuaries were extracted. The estuaries to GUI interaction mapping is a time-consuming task. Therefore, we worked with 10 bug reports containing 49 individual estuaries. 2 authors first independently worked to get the ground truth data and then discussed between them to resolve any disagreements and come to a conclusion. We compared 3 different prompts in terms of F1 score. Zero shot template performs the best compared to few shot and chain of thought for estuary sentence identification. The false positive and false negatives are the minimum in zero shot setting. In terms of F1 score, zero shot template performs the best compared to few shot and chain of thought for individual estuary extraction. Although true positive and false negatives are same across all 3 types of prompts, we get the minimum number of false positives for zero shot prompt. Here, 39 individual estuaries were considered on a few filtering criteria. In terms of F1 score, the zero shot template performs the best compared to few shot and chain of thought for estuary to GUI interaction mapping. Here, the first step is identifying the correct screen, and the second step is identifying the correct interactions. In all 3 types of prompt, for identifying the correct screen, the hit rate does not differ much. However, for the interaction hit, zero shot achieved a hit rate of 76.9%, outperforming the other 2 types of prompts. Although few shot and chain of thought are designed to improve performance, in our case we observed that they added noise to the data. In a zero shot prompt, we provided only the task description and generated output. In the few shot prompt, we provided examples relevant to a specific task, and in the chain of thought, we provided rationale for each of those examples. Ideally, few shot and chain of thought are designed to improve the quality of the generated response. However, in our case, we have seen that zero shot performs the best. The reason for that is that few shot and chain of thought for few shot and chain of thought, GPT-4 has to process a lot of text, and therefore the generated response contain noise. To evaluate the performance in our approach, we ask 2 research questions. So first one is, what is the effectiveness of assigning quality annotations? Then, how many missing estuaries were identified correctly? We compared our approach with Euler, as this is the state of the art for assigning quality annotations to estuaries. These approaches use a simple natural language techniques for mapping steps to reproduce to GUI. To evaluate the performance of our approach, we utilized a dataset containing 21 bug reports from 5 mobile applications. In the identification phase, we identified 73 S2Rs, and in the extraction phase, we extracted 82 individual S2Rs. Two annotators participated in this phase and they first independently worked and discussed to resolve any disagreements. Four individual S2Rs were discarded because of the rotation action. In the end, we ended up with 70 correct steps, 7 ambiguous steps, 1 vocabulary mismatch, and 38 missing step annotations. Missing step annotations are applied to those steps to reproduce that require filled missing iterations. We identified 158 missing S2Rs in our dataset. Now we describe individual S2R annotations for all 4 annotations that we used. In all cases, AstroBR performs baseline Euler in terms of F1 score. In all annotation, AstroBR produces less number of false positives and false negatives. For correct steps, the F1 score is 0.957 for AstroBR, and for Euler it was 0.857. For AS, it is also the F1 score is much higher than Euler. For missing steps, the F1 score is 0.769, whereas for Euler it is 0.575. For VM, the F1 score is 0.500, and for Euler it is 0.143. Overall, the F1 score for AstroBR is 0.879, and for Euler it is 0.702. So AstroBR outperforms Euler in assigning quality annotations by a relative improvement of 25.2% in terms of F1 score. Missing S2 results for Euler. Here the missing score was for Euler the F1 score for missing S2 results is 0.373, and for AstroBR it was 0.639. So AstroBR outperforms Euler in identifying missing S2Rs by 71.4% in terms of F1 score. We also investigated if the identified missing S2Rs are different compared to Euler. AstroBR generates less number of unnecessary missing S2Rs, that is 56, compared to Euler, which generates 190 missing S2Rs that AstroBR fails to generate. Moreover, AstroBR identified 49 missing S2Rs that Euler fails to identify, whereas Euler identified 28 such individual S2Rs that AstroBR fails to identify. All of our replication packages are available in GitHub and Zenodo. We suggest those interested to check out our replication packages. Thank you, and I'm happy to answer any questions.